Hey everybody, welcome to the 6th grade science podcast. This is Miss Brown and Miss Butterfield. We're going to talk to you guys today about surface currents, deep currents, and how it affects the weather along the coast. So first you need to know what an ocean current is. Basically, guys, we've got our vast ocean, and inside the ocean we have a stream. And those streams are either going to be a surface current, that's located near the surface, or it could be a deep current. First, we're going to talk about surface currents. There are three big things that make a surface current move in the first place. The first is global winds. So winds blowing across the ocean that cause the water to move in a certain direction. Now, global winds, it's important to remember that global winds aren't like winds that you're going to find in your backyard or anything. These are big, massive winds that are constantly blowing in the same direction all year long. So these global winds have a major impact on our surface currents, pushing it in the directions that it does. So if you remember from our lab this week, the aluminum ball that was floating at the top of the water, when blowing in the straw, you were able to move that aluminum ball around, representing the surface current and how the wind blows the surface current around. Next is the Coriolis effect. The Coriolis effect, it's the apparent curving of moving objects from a straight path due to the Earth's rotation. So basically everything in the northern hemisphere, when it's moving, it's going to be curving, it's going to look like it's curving to the right, and then everything in the southern hemisphere, it's going to look like it's curving to the left, and that's due to the Earth's rotation, and that's called the Coriolis effect. If you remember from our lab, when you were spinning the manila circle around and dropping the water droplets on it, you were able to see that by spinning something, when you were done spinning and you looked at the manila circle, you were able to see the curved path of the water droplets. And the third thing that moves a surface current is called continental deflection. And basically that's like when the ocean current runs into a continent or it's getting close to a continent, it has to change direction. It's not going to go through the continent, so it's going to get close and it's going to deflect or change directions. And our lab was the petri dish. So our petri dish was representing our land, and the food coloring that you blew toward the petri dish, that represented global winds impacting surface currents and how the surface currents would go around the petri dish or around the land. All right, so let's take a look at our surface current map that we have here. Let's look down here next to South America. We've got a lot of currents going on there, and if you look at the South Equatorial, the one here, it's going toward South America, but then all of a sudden it takes a turn to the left. Okay, it's turning to the left, it's in the southern hemisphere, but also because South America is in the way. So we've got the Coriolis effect telling it to turn left, and then we've got South America being in the way, so continental deflection turning the current to the left. You also see up here in the northern hemisphere, we've got the California current. The California current comes off of the poles, comes down from the poles, headed toward the equator, and it curves across California, the California current there. So when we're talking about surface currents, there's warm water currents and then there's cold water or cool water currents. And remember, we're talking about surface currents, so it's like the water that you would go swimming in. Warm water currents, because it's warm, the air above it's going to be warm, so it's going to bring warmer air, warmer moisture to the coastal cities along a warm current. So that's pretty simple to remember. If it's a warm current, it's bringing warm air, warm moisture to the coastal city. If it's a cool current or a cold water current, it's going to have the air above it that's going to be cold or cooler, and it's going to create some cooler areas along the coast. So let's take a look back at that global map again. Let's pay attention to North America. We've got our Gulf Stream that's very, very important in our global conveyor belt. It's bringing in warm moisture from the equator. We've got our North Equatorial that's going up toward North America, turning into the Gulf Stream, bringing that warm moisture to the eastern side of the United States. So let's pick North Carolina here. Let's remember that spot on the map. Now we're going to go same latitude. We're going to go to the west side. We're going to go to California. Now in California, it has a California cold current running next to it, so that's going to be a lot cooler over there. Even though they're at the same latitude, it's going to be a lot cooler over there because of that cold California current. So remember, warm currents start at the equator, and they're going toward the pole. And those cold currents, those cold surface currents, start at the pole, and they're going toward the equator. So they're always headed in the opposite direction of where they originated from. So equator, warm, headed toward the poles, cold. If they start at the poles, they're cold. They're going to head toward the equator where it's warm.
All right, now we're going to talk about deep ocean currents. Deep currents are stream-like movements of ocean water located far below the surface. All right, here's a picture of our deep currents, and this is kind of known as the global conveyor belt. Remember, you've probably looked at a conveyor belt before, or you could think about a belt that runs your car, like the timing belt. It runs and it loops through all these different parts, but it's all connected and it continuously goes from one place to the next. Without it, things don't move like they should. So think of your bicycle chain. It loops around and around and around and around, and it's continuously moving when you're moving. If your bicycle chain falls off, you're not going anywhere on your bike. And so it's the same thing with cold water and warm water on our globe. Deep currents are incredibly important to our climate. So there are some things that affect the deep current. The first is temperature and density. So when the warm water is brought to an area by the surface currents and it's taken to the polar regions, they get cold. Just like you, when you get cold, you all scrunch up. Well, so do the water atoms. When they get cold, they get together, they get close, and it makes them more dense. When it's dense, it drops down, and then it's moved to another place. When it gets to that warm place, it's going to rise back up, and it's going to move toward the polar regions. And so you have this repeating loop of things warming up and cooling down. But temperature has a huge effect on density. When you did the lab, you may not have seen it quite as clearly as this, but this gives you a great visual of what you felt when you touched that graduated cylinder. At the bottom, you had the blue cold water, and at the top, you had the hot red water. And it's because warm water is less dense and it rises to the top. Blue water was cold, and so it sunk and stayed at the bottom. All right, salinity also has a huge impact on density. Salinity is the amount of salt dissolved into a liquid. The more salt, the more dense. So how does some water in the ocean become saltier than other water? Remember, there are two ways. But let's look at this picture first. This may have been the most dramatic moment of the lab, when you bent down and you looked at that water and you realized that all that green salty water was so dense that it sat at the bottom of the beaker. Even though you poured it in last, it sunk straight to the bottom and it hung out there together because that salty water is much more dense than the fresh water. All right, here's the first way that water becomes saltier. It's through freezing. The water freezes at the surface, but the salt doesn't freeze with it. It's kind of squeezed out and back down into the water below. Water molecules, when they freeze, they expand because water is an amazing thing, and they float up to the top. But all that salt is down there in the water below it. That water becomes more salty. It has an increased salinity that makes it denser, and then that water sinks. The second way that water becomes saltier is through evaporation. When it's in a warm place near the equator, that water evaporates because of the sun, but the salt does not evaporate. The salt stays in the water that's left behind, and it has a higher salinity. When it has a higher salinity, it becomes more dense and it sinks. And this is actually what starts the Gulf Stream. Is there in the equator, the water evaporates, the water becomes more dense, and it sinks, and it gets that hot water moving.
All right, guys, just to recap the three ways that surface currents moved. We've got continental deflection, we've got the Coriolis effect, and we've got global winds.
The three ways that deep currents move are through increased salinity through evaporation, increased salinity due to freezing, and increased density due to temperature.
Good luck on your quiz.